Okay. 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 We're beginning now to do stoichiometry all over again. How about that? But now we're going to deal with solution stoichiometry and solutions in general. And so I want to be pretty basic in the beginning. Um, and we'll talk about a solution is made of two components. There's a solute and a solvent. Now, the technical definition of the solvent, it is the component of the solution whose properties most resemble the solution. Now, um, most of the time, whether something is a solute or a solvent is pretty easy. I mean, if I put sodium chloride into water, and water's the solvent, and sodium chloride is the solute. If I mix alcohol and water, I've got a little bit more of a problem. Alcohol and water miscible in any proportions. So if I took a, a glass of water and put a tablespoon of alcohol in it, it's pretty easy to predict that the solvent was the water and the alcohol was the solute. But suppose I had a glass of alcohol and I put a tablespoon of water in it. Now the alcohol is the solvent and the water is the solution, the solute. Now, when you get into that gray area in the middle, then how would you know? Well, technically, if you measured, say, the density of the solution and measured the density of water and the density of alcohol, the solvent would be the one whose density was closest to the solution. So it's seldom we really have to make that detailed, precise definition. Most of the time, it'll be obvious that the uh, one is higher in concentration is the most. And now the concentration of the solution is the amount of solute dissolved in a given amount of solvent. Now, there are a couple of ways of measuring concentrations. The one that we're most familiar with is molarity. You've used that already several times in problems, um, so this is not unusual. In high school lab, uh, you probably dealt with some molar solutions, and if we had been in lab, you would have dealt with several of them in our lab as well. But the thing I want to impress upon you is that molarity is the ratio of the number of moles of solute to the volume of the solution. It's what you get when you divided two numbers out. When you get a bottle of hydrochloric acid and it says 6M on the front, it doesn't mean there's 6 moles in that bottle. What it means is if you took the number of moles of HCl in the bottle and divided by the volume of the solution in the bottle, you would get 6. And that's all it means. It's a ratio of two numbers. Now, if I have to divide two numbers out, there is one number I really like to do long division by that number. You got any idea what that is? 1. I can divide by 1 in my head. Ain't I smart? So if molarity is a ratio that I took two numbers and divided out and say got 6 for 6 molar, then I can imagine that my volume was 1 liter. And then that would mean it was 6 moles. Now, it wouldn't be in that little bottle, maybe, but the ratio is still correct. And I can do my calculations based on that ratio. So anytime I've got a choice of what the volume is going to be, I'm going to make it 1 liter. And we'll use that to simplify problems as we go along today and in the future. So it's a ratio of two numbers. It's the number of moles of solute divided by the number of liters of solution. And now this is a more useful relationship for us. Just cross multiply the volume of the solution in liters times the molarity is number of moles. Now, when I'm doing reactions, you remember the balancing coefficients, we can express them in moles. And so if I'm talking about volume, volume for a given molarity, volume is proportional to the number of moles. I always tell students, wouldn't it be nice if we had this magic scoop and we could just scoop it into anything and it would take out a mole? Wouldn't that be good? You know, if I've had NaOH and H2SO4, I need 2 moles of NaOH with 1 mole of H2SO4. So I could take my little magic scoop, I could stick it into the H2SO4 solution, take out 1 of them, and I could go to the NaOH and take out 2 scoops, and that would be stoichiometric. And everything would be used up. Reaction would be exactly what I want it to be. Well, in molarity, we have just that. If I had a 1 molar solution, 1 liter, my scoop, would take out 1 mole. Or if I needed 2 moles, I'd take out 2 liters, 2 scoops. So volume is proportional to moles and molar concentration. And we make use of this a lot when we're doing calculations. Just keep that relationship in mind. Volume in liters times molarity is moles. And that'll help us a lot in our calculations. Now, suppose we're diluting a solution. All we've done is added water to it, right? Add solvent. In most of our cases, they're aqueous solutions. So the volume of the concentrated solution that I had before I put any water in it times its molarity would have to equal to the volume of the diluted solution after I've added the water times its new molarity. So this is a relationship we use a lot of times when we want to dilute solutions and get a new molarity. We'll use this relationship. Since volume times molarity is moles of solute, that didn't change when you put water in it. So that's why this relationship works. Now, when you put ions in water, they dissolve and if it's soluble, if the ionic compound is soluble, and we know how to determine that, right? Solubility rules. So that if it's soluble, it's going to produce an electrolyte. And current is carried by the movement of cations toward the cathode and anions toward the anode. Now, that's where the names come from. And if the cation, what charge is it? Positive, that's right. If it goes toward the cathode in that particular cell, then what's the charge on the cathode? Well, if the cation's positive, it's attracted to the cathode's negative in that case. Now, that's how the names of the ions came about. Cations and cathode and anions and anode. But we're going to modify that definition a little bit later on, because sometimes the sign of the cathode might not be what we think it is. And we'll talk about that when we get to electrochemistry in Gen Chem 2. Now, you can't put free electrons into water. If you put electrons into water, there's really no place for them to go. What's going to happen is the electrons are going to actually have such a high, the electric field of a charge is determined by the size of the charge and the volume that the charge is in. When you're talking about an electron, you're talking about a fundamental particle with a diameter of roughly 10 to the negative 13 centimeters. So it's a very, very tiny particle with a total -1 charge on it. That produces such an electric field, it's going to drag the water molecule it's going to accelerate it right toward that negative charge. And when it gets there, the positive part of the hydrogen is going to hit the electron. That's where the positive charge is on water. Remember when we talked about the dipole moment, the oxygen is the negative end of the water molecule and the hydrogens are the positive. Well, that electron is going to go piling into that hydrogen atom on water, and it's going to grab it so tightly that that positive ion will pick up the negative electron and become a hydrogen atom. So we do, when you put electrons into water, you do a process called electrolysis. So what's going to happen is the electron will just disappear. In its place will be a hydrogen atom, and and in its place will be a hydrogen atom, and the OH ion would be left in its place. So this negative electron goes in and produces a hydroxide and hydrogen. So it electrolyzes water. And that's one of the ways we can make hydrogen, is to pass an electric current or electrolyze water. And a lot of people think that's where we get hydrogen. It really isn't. We get hydrogen when we make gasoline. You have to break up the molecules, and the temperature and everything that you have to use to take crude oil and make gasoline out of it breaks off a lot of hydrogen atoms. And those combine together and make H2 gas. And it's a byproduct. We're trying to make gasoline, but we get hydrogen as well. And if you've ever been around a refinery, you might have noticed that somewhere in the middle of that refinery, there's a pretty big stack. And most of the time, you'll see a great big long flame, maybe 10, 15 feet tall, burning. They're burning off the extra hydrogen because its market value is sometimes not worth trying to recover it. So they just burn it off. But that they do collect enough hydrogen that way to supply the demand for it and burn off the rest of it. So we don't get it by electrolysis of water. That's what a lot of people think. They think they're really doing good by having a hydrogen or something like that run their car. Well, guess what? When you plug that in to the power plant to get your electricity or whatever, you're burning fuel at the power plant. And you may think you're not polluting, but you are. It's down at the power plant where that is occurring. And if you think you can use hydrogen, just go buy a tank of hydrogen and run it in your car. You sure can. And they have. The MTSU's got a car that runs on hydrogen, maybe more than one now. But it's not saving crude oil. It's actually using more. So go figure. All right. So, but anyhow, the electrons cannot exist in water. If you put electrons into water, they will decompose the water. Now, what about a proton? Well, a proton is also the same size as an electron, almost exactly the same size, and carries a positive charge. So it's going to have an awful large electric field around it. Well, the water molecule sitting over here, the oxygen end is negative. Now the proton is going to go pulling that water molecule straight into the proton, but what's going to hit? The pair of electrons on oxygen. The pair of electrons then are going to be attached to that proton you just added, and now you're going to have 3 OH bonds. You're going to have H3O plus. That's an acid. So H plus can exist in water. We write it as H plus acid, aqueous, and that means it's really H3O plus and H5O2 plus and H7O3 plus. There'll be lots of water molecules attracted to that one proton that we put in. But the most dominant one is H3O plus. So in the case of a positive charge, a proton, we can put those into water and not decompose the water because the water has a pair of electrons to accept it. And it's actually good for us because it allows us to have acids. We don't decompose the water when we put protons in it. Okay. Now, when you do hydrate an ion, you're going to attach water molecules to it. And anytime you put an ion into water, we write Na plus aqueous. Well, the Na plus ion is in there, but it's probably not very much of it, if any at all. That's just a free Na plus ion. Instead, typically ions collect 6 water molecules around them, is not uncommon. And the sodium ions in there is going to have right attached to it an octahedral arrangement of water molecules sticking onto the H plus. So it's going to hydrate it. And those stick on pretty tightly. And so when that sodium ion needs to move through water, now all of a sudden its size has increased because it's got that shell of water molecules around it. So it's bigger, and it's going to, if there are another ions around close by, them being hydrated also weakens the force holding the ions together. So if I got a Na and a Cl minus, the way it dissolves is the water comes in around the corner of the crystal where maybe there's a sodium ion sitting there. The water molecules hydrate around the sodium ion and weaken the force between, it gets bigger, weakens the force between it and the chloride ions that are there. So it can drift off, and then the water molecules can go in and flip over the other way, hydrate around the chloride ion, and it slips off and goes out into solution as the hydrated ion. And even if they bump into each other out in the solution, the concentration is low. They're not going to do ion pairing much. Might have a little at real high concentrations, but most of the time you've weakened the force enough that the ions just saturate and just dissolve and go into the water. So the hydration, increasing the size of an ion, is what causes a lot of them to weaken that force enough to be soluble. So in our solubility rules, those are the ones that are soluble. Now, when ions move through solution, they're going to have to move the solvent out of the way. If I'm going from point A to point B in the solution, I've got to move that ion all the way from point A to point B, and it's got all these water molecules stuck onto it, and it's going to have to push the other water molecules out of the way. So it's going to slow the migration. So the tighter, the more hydration you have around an ion, the bigger it is, and the slower it will migrate. It'll still migrate from one place to other in the solution. It's just diffusion in liquids happens, but it's slow. Yeah, some of those interact so strongly with the water that it does dissolve in the water, and that was the solubility rules that we talked about. Now, molecular compounds. How do we distinguish ionic from molecular? An ionic compound is going to be typically a metal with a non-metal. The most ionic compound you could make would be from the lower left-hand side of the periodic chart, those elements like cesium, and then the higher elements on the right of the periodic chart, the furthest one over there is fluorine. So maybe neglecting francium, the radioactive group 1, cesium fluoride would be the most ionic compound you could imagine and would have the strongest force of ionic attraction between them. So the cesium fluoride, it's probably going to dissolve fairly easy in water, I would guess. Okay, and the closer you get them together, then maybe you don't get a good ionic compound. The rule we had was if the difference in electronegativity between the most metallic element and the most non-metallic element in that formula, that difference needs to be about 2 or greater to have an ionic compound. If you're below that, the bond is not going to be ionic, it'll be polar covalent. unless the two electronegativities are the same, and then it would be purely covalent. So molecular compounds are going to generally be between nonmetals and nonmetals. And the electronegativities are so close together that you might have polar bonds all right, and would, but they would not be ionic and they would not separate in water. We're going to learn in Gen Chem 2, we'll talk about this right in the very beginning, about why certain things dissolve in each other. And molecular compounds will not dissolve in water very well, most of them. But some of that looks similar to water. For example, I told you alcohols will dissolve in water in any proportion. They're miscible in each other. Well, think about the molecular structure. CH3OH is methyl alcohol, but water is HOH. So the only thing different is you've replaced a hydrogen on water with a CH3 group. So it's the one end of it still looks just like water. So when you put alcohol and water together, it doesn't look like there's a difference in environment very much. The alcohol that was associated with other alcohol molecules and the water molecules that are associated with each other, they would just as likely be associated alcohol to water as they would alcohol to alcohol and water to water. And so they mix together. Now, if I put something like oil, you know, oil and water don't mix, they say, right? Okay, if that's true, the reason for that is the oil molecules are totally different from water. They would rather interact with themselves, and water doesn't want to interact with those non-polar oily type things. And so the water stays associated with itself, and the oils molecules stay associated with themselves, and they separate according to density. If the oil is more dense than water, it would sink. Some crude oils do. Or if it's just light machine oil, it'll float on top of the water. And we say they don't mix. Well, I'll tell you what you do. You go get your Coke and go out and take the dipstick out of your motor, out of your car, and swirl that dipstick in your Coke, and then put your straw back in there after you get all mixed up and you say the oil's going to float to the top. Well, put your straw in there and take a sip. I think you'll not want it. Everything dissolves in everything a little bit. And that's going to be a discussion of Gen Chem 2 as well. So molecular compounds don't dissociate into ions when you put them into water. Typically, they stay together. And the molecular compounds are the ones that are not ionic. And that would be the ones whose electronegativities between their atoms is less than 2. Now, acids, I told you a while ago, are formed by taking a proton and putting it into water. If I take HCl and put it into water, for every mole of HCl I put in, I'll make a mole of hydrogen ions that will attach to water and make H3O+. So the acids, HCl is a molecular compound itself, but when I put it into water, it can transfer the proton to the water and dissolve. And it does up to about, I don't know, 36%, I think, or something of an HCl solution can be HCl. That's what we call concentrated hydrochloric acid. It's saturated with HCl gas in that solution. And it's, I think, 12 molar is the most concentrated HCl solution that we can get, 12 moles per liter. And that H3O plus is what makes an acid an acid. So if I put hydrochloric, hydroiodic, hydrobromic, nitric, sulfuric, perchloric acid all into water, they all do exactly the same thing. For every mole I put in, I'll make a mole of H3O plus. And so they're all equivalent strength in water. And they are the strong acids that we talked about. But if I put acetic acid into water, then I'm going to get some H3O plus. Usually about 5% of the acetic acid I dissolve in water actually dissociates to create acid. That's why we call them weak acids. And they don't produce as a complete complement or mole per mole of hydronium ion that they would from the original solution. So if I take HCl and water, it goes completely. We're going to start looking at reactions that can go both ways. We've already done that a little bit with the single and double replacement reactions. They can sometimes go either way, but not both ways. We're going to learn in Gen Chem 2. I just told you a fib. Everything does go both ways a little bit, but we'll clear up that fib in a later story. Now, again, you can't have free protons in the water. They would destroy the water if they were free protons, but as soon as they get over to the water, they attach themselves to the lone pair on water and produce hydronium ion. So you're not going to have free protons in water, but sometimes instead of writing this H3O plus, we get a little sloppy and we just write H plus aqueous. And that doesn't mean the proton actually exists in aqueous solution. It means that we just got lazy and didn't want to write H3O plus and H5O2 plus and H7O3 plus and so forth. Those are the 6 strong acids. We've talked about them already. You know what they are. And hopefully you've got them memorized already. Then all the other acids that's not in this list is a weak electrolyte. Now, if hydrogen is the first component of a 2-element compound or with a polyatomic ion, then it's certainly an acid. And if it's one of these ions, it's a strong acid. If it's not, it's a weak acid. They only partially dissociate in water. Now, what about bases? The group 1A and group 2A metal hydroxides are soluble. Remember solubility rules for hydroxides? All hydroxides are insoluble except group 1 and group 2. And actually some of group 2 don't dissolve very well. But these are the strong bases. And anything else that produces hydroxide ion in water is just a weak electrolyte. So there can be some soluble, some slightly soluble hydroxides, and they would be weak electrolytes. They would not be from group 1 and group 2. And then there are other compounds like ammonia. When you put ammonia into water, NH3 and H2O will make a little bit of NH4OH in the solution. So it is a weak base, and it produces a little bit of ammonium ion and hydroxide, comparable amount, equal amount of hydroxide ion in the solution. But if you put ammonia into water, it will dissolve up to about 15 moles per liter. And that's strong. That's the strongest base you can get, but it's still 15 molar ammonia. If you were to open a bottle of concentrated ammonia, that's what we get out of the stockroom as the most concentrated we can buy. That stuff will make you cry your eyes out from 2 or 3 feet away sometimes. You get it on your hands or on your clothes, it's going to, well, it's also smelling salts. You know, if someone passes out, there's a smelling salts you can get, a little capsule you can break and hold it under their nose. And if they're not dead, they'll get up because it's a really pungent odor. And but you don't really have ammonium hydroxide. I have seen bottles labeled in the laboratory ammonium hydroxide. Well, That's not quite true. There's a little bit, maybe 5% of the solution is ammonium ion and hydroxide ion, but 95% of it is just dissolved in H3 in the water. That's just the way all weak electrolytes do. So ammonia is weak bases. So you get about 5 pairs of ions for every 100 molecules of ammonia dissolved. I told you it's about 5%. So sometimes to show that, we show a double arrow, and sometimes we would make the arrow to the right little tiny and the arrow to the left great big, showing that it mostly on this side. And that'll we'll take that into account in Gen Chem 2 especially. We'll talk about that relationship. A neutralization reaction is just an acid reacting with a base. Each one destroys the properties of the other one. Acids have a certain set of properties. They react with metals to produce hydrogen in some cases. They have a very strong odor, and they generally have a taste like vinegar. Vinegar is the taste of acetic acid. All acids would have a slight vinegary-like taste. It would be reminiscent of that. Bases they neutralize acids. They have a lot of chemical properties that are opposite to those of acids typically. So they do neutralize each other when you put an acid and a base together. What you're going to make is what we call a salt and water. So this is a generic reaction for any acid with any base will make a salt and water. Now, if this is hydrochloric acid and this is sodium hydroxide, it would make sodium chloride and water. And that's what we refer to as table salt, sodium chloride. But any cation that's not hydrogen with any anion that's not hydroxide is a salt. If it's a hydrogen, it's an acid. If it's a hydroxide, it's a base. And if it's neither, it's a salt. So salt is just a generic term for any cation with any anion, except the cation can't be hydrogen and the anion can't be hydroxide. Now, if I put HCl into water, you don't have HCl aqueous. That would be incorrect. It doesn't really exist. When you put it into water, you're going to completely convert to hydronium ion and chloride ion. For every mole of this you put into water, you get a mole of this and a mole of this. So all the strong acids can't be really written as HCl aqueous. Sometimes we might do that in a molecular equation, but if we were trying to show what the ions are, instead of that HCl aqueous, we would replace that with H3O plus aqueous and CO minus aqueous. Now, when you write down the equation for a reaction, you can convert to the ionic equation by just going into each species, and we've done this already. And if it's soluble, you separate the ions. If it's a strong acid, you separate the ions. If it's insoluble, you leave the compound together as a solid. And if it's a weak base, you leave it together, or a weak acid, you leave it together. Like HNO3, we would separate to H plus aqueous or H3O plus aqueous and NO3 minus aqueous. But HNO2 is a weak base, and we would just write that as HNO2 aqueous. And then once you've got all the ions present, then you can separate the ions and then look on the left reactant side and the right product side and cancel out any species that are the same on both sides. And that would leave behind what we call a net ionic equation. And back when we talked about double exchange reactions, some of them we said there was no reaction because all of the reactant ions were soluble and all the product ions were soluble in any combination. And we said that you didn't get a reaction. Well, if you did those reactions and wrote their ionic equation, you would see that every ion on the left appears also on the right, and they would all cancel out. So if your net ionic equation does not exist, then that reaction doesn't occur. And so that's one of the ways you can formalize and tell whether a particular reaction takes place or not. Okay, here's some problems. What's the molarity of a solution made by adding 50 grams of AlNO3 to 500 milliliters of water and diluting to the mark? Okay, now what is molarity? See, that's what's asked for in the problem. First thing we should write down is the definition. So now that gets the relationship that is appropriate to this problem. And when I said, what is the molarity? I think this. Now, my job is to put in numbers in the numerator and numbers in the denominator and divide them out. So I got to get the number of moles of this, and we remember how to do that, right? If you take the given number with the given unit, put this unit down here, put the unit I want up here, moles, and 1 mole of this compound weighs 213 grams. So if I do this math, that gives me my answer for the number of moles. The number of liters of solution is 500 milliliters, so that would be 0.5 liters. Now, actually, sometimes in order to not make a terrible mistake, what I will do, instead of just moving a decimal point, I moved it in the right direction there. You know, on the pressure of a test, I might not. I might do something really silly and move the decimal point the other way. But if I go back up here and write that as 500 times 10 to the minus 3 liters and put that in for the volume and divide that out, I'm not going to make that mistake. So I showed you converting this, just moving decimal points, but in reality, I seldom do that. I most always will just replace milli with what it's equal to. It's 10 to the minus 3. So 500 times 10 to the minus 3 is 0.500. But if I do it 500 times 10 to the minus 3, I have not done any conversions. I can't have made a mistake. If I put that number in there, I'm going to still get this number. And it's less likely to make an error. What volume of 6 molar aluminum nitrate has 5 moles of nitrogen in it? Okay, now, what was given in the problem? 5 moles of nitrogen. What I want? Volume of solution. Okay, now, if I look at this compound, it's got 3 moles of nitrogen in it. And it's in 1 mole of that compound. Now I'm going to put another factor on. I've got moles of compound, but it asks for volume. All right. I know in this solution there's 6.50 moles of the compound in 1 liter. So I'm using my conversion factor, as my molarity, as another conversion factor. And string them together. There's my math. I did the answer. But do you see the method? A number with a unit, number with that unit. Put that unit here. Convert to what I can. That's what I did. I said the compound has 3 moles of nitrogen for every mole of the compound. Now I would look at my units and I say, okay, my answer is in moles of that compound. That's not what it asked for. So I got to get rid of that unit. I'll put it in the denominator here. I'll put the unit I want here if I can do it. And I can. 1 liter of the solution has 6.5 moles. And now I can cancel them out. You see how this now is just like we did when we converted centimeters to inches? Maybe instead of centimeters to inches, we're going centimeters to feet. We added another conversion factor. That's all we've done. The method is still the same. And if I looked at my multiple choice answers and I didn't I found it in milliliters, then I could just convert this to milliliters and get the same thing. Remember, 256 times 10 to the minus 3 is the same thing as that. Okay. What volume in milliliters of 6.5 molar aluminum nitrate has 1 gram of oxygen in it? Now, believe me, there are a lot of people from high school and other ways would work this problem in a long, drawn-out, awful way. Look, what is our method? What's given in the problem? 1 gram of oxygen. What I want in the denominator of my factor, grams of oxygen. Okay, if I look at this compound, there's 3 of the nitrates. Each nitrate has 3 oxygens, and the atomic weight of oxygen is 16. That's the number of grams of oxygen in 1 mole of that compound. Now, my units cancel. My answer now is in moles. No, it's supposed to be milliliters. What am I going to do? Well, get rid of that unit. 6.5 moles of that compound is in 1 liter of the solution. Now that's going to cancel. And there's my answer. And if I want that in milliliters, it'll be 1.07 milliliters. Okay? What is the molarity of the resulting solution of 250 milliliters of 6.5 molar aluminum nitrate is mixed with 125 milliliters of 3.5? Okay, what's this asking? Molarity. What am I going to do? Write the definition down. I want the number of moles of the solute and the total volume of the solution. Okay, well, I got 2 solutions that's got aluminum nitrate in it. And the total amount is going to be the sum of the 2. Remember the relationship, volume times molarity is moles. So 0.250 liters or 250 milliliters, if I wanted to, times 6.5. That's the number of moles. Volume times molarity is moles. From one solution, there's 125.1250 liters, 3.5 molar. That's the number of moles of solute in the second solution. So that's the total number of moles in the numerator. What's the total volume? 250 and 125 milliliters, or 0.250 and 0.125 liters. Now, we've done this now, putting moles divided by liters. I want to show you, I'll point out to you, a really quick and dirty thing. Look, if I put 250 times 6.5, I don't get liters, moles, I get millimoles, right? So if I have millimoles here and milliliters here, it's the same answer, isn't it? Milli's going to cancel out. Milli is 10 to the minus 3. So if I've got this and I express it in milliliters, and I express a millimoles, and I express this in milliliters, I don't have to do that conversion there at all. It still gives me exactly the same answer. So this would be 5.5 molar. Now, while we're here, whenever you work a problem, there's always many, many ways of making mistakes. So you ought to always check your answer and see, does it make sense? Okay, well, I got a molarity that's 5.5. One of the solutions was 6.5 and the other one was 3.5. Should the answer be between those 2 numbers? The answer is yes, yes, it should be. If I made a mistake up there somewhere and moved decimal places wrong or did something, I might come out with a molarity that was bigger than the biggest one or smaller than the smallest one. Those answers would be wrong. That should tell me right away I've made a mistake. Now, this would be, okay, no, not so, I can tell. If I look at this, I've got more of this solution than I have of this one. And the molarity of this one is bigger than this one. In this case, I know my answer is going to be closer to 6.5 than it is to 3.5. So that makes really, really good sense. So always when you're writing answers down and you're getting ready to put them in on the test or something, check to see if the answer makes sense. If it doesn't make sense, it's probably wrong. And you can, even though it might have one of the foils, might be that answer. So maybe if it's a mistake, it's very, very common, I may have coded for that in the test. So you could very easily come out with a wrong answer that is one of the answers on the test. It's just not the right answer. What volume of water should be added to 250 milliliters of 6.5 molar if you want the solution to be 4.25 molar? Molarity is moles over liters. Volume, okay, well, we've got 0.255 milliliters of 6.5 molar. I'm going to add water to it. And I want the molarity, volume times molarity is moles, I want the molarity to be 4.25. I can solve for the volume of the diluted solution. So it has to be a volume of 390 milliliters, or 0.390 liters, if that's going to be the molarity is 4.25. Now, there's a little tricky problem. It asks for how much water, so 390 is not the answer. That might be one of the answers on the test or quiz, but it's not the correct answer. The amount of water, we have to subtract the 255 from the 390 and get the amount of water. We have to add 135 milliliters. So that would be the correct answer. 390 would be the wrong answer. Here's a checkpoint on this. Let's see what it looks like. Yeah. Okay. Maybe I will stop and go over to the pad with you, and a bunch of cords in the way. Let's see if I got a pen. Oh, I can't write with it. I've got to write with this. Okay. Now we've got 25 milliliters of 4.55 molar. My pen, that pen is dead. Let's try this one, see if it'll work. And the compound is UO2 3 PO4 3. Okay. Now, what it's asking is I've got that, and I put it into 150 milliliter volumetric flask. Now, just to remind you, this one looks a little weak too. Maybe I got a better one. I want to remind you what a volumetric flask is. They all look something like this. They've got a bulb down here at the bottom, and then across the top up here, they've got a little line. And whenever, let's say this is a 150 milliliter flask, whenever you, if you thermostat this to the calibration temperature for that flask when you bought it, I think ours we usually buy is 25 degrees C. Lab is not usually 25. That's a little bit warm for us. So it's probably around 22 in the lab, but if you thermostated this to 25 degrees C, and then you fill it so that the meniscus just touches that line in one point right there in the middle, that's probably got 150.000 milliliters. It's one of the most accurate ways we have for measuring volume is in a volumetric flask. And even though it says 150, that's not two significant figures. That's probably at least 5 or 6 significant figures if it's in a volumetric flask like that. So we're going to put this into that volumetric flask, and we put 25 milliliters of that molarity into it. So once we start out, we're just going to have like 25 milliliters down here in the bottom, and then we're going to add water and dilute it to the mark. So what's going to be the molarity? What's the concentrated of this? What's the concentration of this diluted solution? Well, it's 25. I would wish I'd put another decimal point on there. Times 10 minus 3 liters times 4.55 molar. Well, maybe it'd be a day to start cleaning up some old pencils. Some more back here. All right, let's try this one. Okay, so that's going to be the number of moles. Okay, let's do the math and see what we get. 25 with an exponent that's minus 3 times 4.55. This is 0.11375 moles. Molarity is number of moles in number of liters. 150, well, it's times 10 minus 3 liters. So if I take that number and divide by 150 with an exponent of minus 3, I get 0.758 and 333 like that. And like I said, two significant figures is really all I'm supposed to have. It's 0.76 molar would be the concentration. Now, the second part of the problem, that was number 1. The second part of the problem is what mass, I'll just say grams of uranium, what mass of uranium per milliliter in 0.0545 molar UO2 3 PO4 3. Okay, so I want to know how many grams in milligrams, it said. Milligrams, how many milligrams of uranium per milliliter? So if I put milligrams over milliliters, millis cancel, right? That's the same thing as grams per liter. Now, I just showed you that because we talked about this already. You can use, as long as I'm consistent, if I have milligrams and milliliters, that's going to give me the same result as grams per liter. Now, so this problem would be easier worked if I did this in grams per liter. So I want to, I've got I want 1 liter of my solution, and I want to convert from liters to grams of uranium. Okay, look at my concentration. If it would have this many moles per liter of the solution, so the number of moles in 1 liter would be 0.0545 grams in one of the compound. And now I want to go from grams of the compound to grams of uranium. Well, we got to get the molecular weight. So we got 3 uraniums, we've got 3 phosphoruses, And I've got 6 oxygens here and 12 there. That would be 18, right? 18 oxygens in a mole of the compound. That would be 3 times uranium is 238.03. 3 phosphorus, that's 30.97. And 18 oxygens times 16. And that would be my mass. So let's do all of our figuring. 3 times 238.03 plus 3 times 30.97 plus 18 times 16. Oh gosh, it's heavy, big one. It's 1,095, 1095 grams in a liter. So there's this many grams in the whole compound. And the grams of uranium is 3 times 238. Okay, so now I got my math. Unfortunately, I'm going to go on and use that factor and then round off to 2 significant figures later. So I'm going to do 0.758. The other digits were 3s, I think. Okay, so, oh no, I'm sorry. I'm fixed right here. I already have that taken into account. So I forgot we're not using that original solution. We're using a different one. So I want to take 0.0545. And yes, 0.0545. And I want to multiply that times 3 times 238.03 and divide it by the answer that I've still got on my screen. Okay, so what I'm coming out with is 0.0355254 and a whole bunch of other digits. And I guess this one I do have 3 significant figures I can use. So it's going to be 0.0355 grams per liter. And now that would also be 0.0355 milligrams per milliliter. Now I did this one on purpose because a lot of you guys are pre-meds. Now, I don't want to scare you too much. This would certainly not be. This is not something you're going to administer intravenously to a patient. You're not going to stick uranium in them, likely. I can't think of a good reason that's not even used as a cancer treatment. So there's nothing you can do with that stuff. But suppose you have, let's say you've got a copper deficiency in a patient. That's not uncommon for this region of the country. Suppose you've got a copper deficiency and you want to treat him. So you get the blood analysis. You found out that his copper level is something below what the normal should be, and you want to bring it up. Now, you're not going to tell him go swallow a penny. You're not going to give him copper metal. You're going to give him a soluble copper salt, and you're going to say, okay, this guy is deficient. Let's say he's deficient by 15 milligrams per kilogram of body weight. You've looked at his analysis. You've got the milligrams of copper he had in his body, and you know how much he weighs. You convert it to kilograms. You got milligrams of copper per kilogram of body weight, And you can figure out then how many milligrams of copper you need to give this guy. Okay, now, then you're not going to do it. You're going to give it to, you're going to give this to the pharmacist. They're going to make up a solution, put it in a bag, and you're going to have to tell them, you're going to have to tell them, you're going to give him, you're going to IV drip this at a certain rate per hour, and at the end of 2 days, you will have administered the right amount of copper to that guy. So you're going to have to do a calculation like this. And then you're going to have to carry it further to figure out, you don't want it to go in too fast and you don't want it to go in too slow. You don't want it to get eliminated before you get your concentrations up. So you've got to figure out the drop rate and the concentration to put in the bag, and then you give that to the pharmacist. They make the solution in the pharmacy. They give it to the nurse and they hang it on the rack and give it to the patient. So this type of calculation is something you might have to do someday. So you need to understand how you go about doing calculations like that. Okay. All right. Now I need to oops, I need to escape out of that so I can get back down here and share screen with you again. Okay. Yes. This one. Okay. Yeah, that's the one we just did. Yeah, okay. You know what? I think it might be a good time to take about a 5-6 minute break, 10-minute break or so. Let's reconvene at 9:45. And I will stop the share and pause the recording so we don't record. We'll start recording. Okay. We're ready to work with solution stoichiometry now. And really, the only thing we're going to do is we're going to make use of this volume times molarity as moles. So essentially, we're going to convert all of the solution stoichiometry to a mole type problem, maybe mole type problem. So let's suppose I've got a reaction and I want to know what volume of 6.5 molar sodium hydroxide would react with 255 milliliters of 5.65 molar sulfuric acid. And of course, we need the balanced equation for that. It'll take 1 sulfuric acid and 2 moles of sodium hydroxide to completely neutralize the 1 mole of sulfuric acid. So we said, what number of moles? So if I take the 255 milliliters of 5.65 molar sulfuric acid, I multiply volume times molarity. I've been consistent here. I'll have a little more to say about this in a minute, but this would be 1441 millimoles, and we want to know what volume, so I'm going to solve in millimoles over here, and then I put in my equation. The equation shows 1,000 millimoles. 1 mole is 1,000 millimoles. So that's the quantity shown in the equation in the unit that was given in the problem. I'm just trying to be thoroughly consistent, okay? And then if I'm looking at 2 moles of sodium hydroxide, that's 2,000 millimoles. So I put it there. Now here is my rebalancing factor. This number divided by this number on the equation. When I set up something like this, my question mark is what I'm calculating. The numbers are what I have given in the problem and given in the example. So where I have a number over a number, that's going to be a rebalancing factor. And so my rebalancing factor is just these divided out. And that gives me 1.441 for my rebalancing factor. Now, what did we do with it? We multiplied by the number that was under the question mark on my problem. So I multiply that by 2,000, and I get 2882 millimoles. So there's 650 6.50 millimoles in 1 milliliter. So that's 443 milliliters when I multiply these out together and then go to milliliters. Okay. What mass of copper is required to react with 50 milliliters of 6.5 molar nitric acid? Well, there is my equation, copper and nitric acid. And solving my problem, I'm only going to deal with the part in the balanced equation that's actually in the problem. That's just copper and nitric acid. The other stuff I'm not concerned about right now. Okay, I want to know how many grams of copper. Well, the equation is showing 3 moles, and the atomic weight of copper is 63.55. So 3 times 63.55 is the number of grams of copper in the balanced equation. I have 50 milliliters of 6.5 molar. That's 327.5 millimoles. 50 times that. And then the equation is showing 8 moles. That's 8,000 millimoles. So I've got a number. This number divided by this one is my rebalancing factor. And it's 0.04. I need to multiply that by what's under my question mark. And multiply that out, and I get 7.81 grams of copper. Okay. See, the only thing we've added is volume times molarity is moles. So we're going to convert the problems all to a mole problem, and then we're going to calculate how much of each thing we've got. How many moles of NO will form if 200 milliliters of 5.50 molar nitric acid is reacted with 25 grams of copper? Okay, again, the nitric acid, copper, and NO, nitrogen monoxide or nitrogen 2 oxide, that's the only things that are involved in the reaction, or in the problem. So I've got 200 milliliters. 200 times 5.50 is 1,100 millimoles. The equation is showing 8,000 millimoles, 8 moles. It's got 25 grams of copper. The equation is showing 3 times 63.55, 3 moles, atomic weight's that. It asks for how many moles. Equation showing 2. How many moles? See, I can read this equation. How many moles of nitrogen monoxide is formed from 25 grams of copper and 200 milliliters of 5.5 molar acid? I can read that problem from this setup. And once I put a number in a unit here, I want this number in that unit here. And the number of grams now that's the unit. I want the number of grams of copper in the balanced equation. It's 3 times that. And if this is moles, that's a 2 mole. So the setup is pretty straightforward and fairly simple when you do this. When you set it up like this, you can see what your rebalancing factors. This number divided by this one is one of them. This number divided by this and this is the other one. And when I do the calculations, I get this rebalancing factor for the nitric acid part. If I do 25 divided by 3 and divided by 63.55, I get 0.1311, okay, which is smaller. There you go. This one is. So that's the limiting reagent rebalancing factor. My answer, that would be multiplying the whole equation through by that number for uh, also. But I'm only going to multiply it by this one because that's what was in the problem. So I multiply that by the 2 moles, and I come out with 0.262 moles of NO. So the answer to my problem is 0.262 moles of NO would form from 200 milliliters of 5.5 molar nitric acid reacting with 25 grams of copper. That would be the moles. What mass of copper is dissolved per milliliter in the solution produced in number 2 above, okay? All right, so we had 7.81 grams of copper was dissolved in 50 milliliters of the acid. So we've got that many grams in that many milliliters. So it's 0.156 grams per milliliter. And I think this is a checkpoint on this. And this is an illustration again. You know, as I mentioned a while ago, you might need to do a copper deficiency. Well, right there is how you get the concentration. Now, this is being grams per milliliter. So if I went that milligrams per milliliter, I just change that to 156 milligrams, and I'd have 156 milligrams per milliliter. And that would give me if I knew how much I wanted to administer, I could tell how many milliliters I'd need to do to get that many grams, and I could cure my patient. Okay, here's another problem on this. What mass of this would form? Let's see. Yes, we need to work that one out. So let's go and do that. Okay. I need to fix it so I can see it. All right. So the reaction, well, I'll write it all out. It's a big one, so maybe I'll turn the page and plan ahead this time and see if this works a little better. I've got 3C3H8. That's propane. If you flick your Bic cigarette lighter, which I hope you don't, that's the gas that's in. Yeah, it's propane. And I really hope, you know, I try to tell you things outside of chemistry sometimes if I think it can help you, but I don't know whether any of you smoke, but I hope you don't. Personally, this cigarettes killed my dad. He lived a decent length. He was 78 when he died, but he died of lung cancer caused by smoking 2 or 3 packs a day. And my father-in-law died of oat cell carcinoma, which is also a really rapidly growing disease. He had the cancer and probably died within, I'd say, 3 months, 4 months of when it was discovered, because that particular cancer that is almost unique to cigarette smokers is, by the time you show a symptom, it's already metastasized and it's filled your lung and it's in your brain and your liver and your kidneys, at least, maybe other places. And it's almost impossible to treat. I'll never forget the look on my father-in-law's eyes. I was with him when the doctor gave him the news. I'll never forget the look on his eyes when he said, "Is there a treatment?" And the long silence and then the no. You don't want that experience for you or anybody you care about. So don't smoke. It will get you eventually. You may think it won't, but it will. If you live long enough, it'll probably kill you. So please don't. 9CO2s, 32 waters, and 10 Cr2O3, that would be chromium 3 oxide. So what mass of chromium 3 oxide, so I'm going to put a question mark over that, how many grams? And the equation is showing 10 moles. and the chromium-3 oxide has 152 molar mass. So we have those numbers in there. That's not my wife, so he can't answer. Nobody can interrupt me in class but her. Okay, we have 1.5 grams of this, and the equation is showing 3 moles, and the molar mass for propane is 44.09. And we're reacting that with 35 milliliters of 6.26 molar chromic acid. Now, I'm going to do a little different than we did over there. I'm going to change this milliliters right here. I'm going to change that to 10 to the minus 3. Now, so that's 35 times 10 to the minus 3 liters times 6.26. Now, this is moles, not millimoles. So now I can just put a 20 down here. And I found people are less likely to make a mistake and easy to do this problem like this. So this is 20 moles. Now, I can get my 2 rebalancing factors. I'm going to take 1.5, divide by 3, and divide by 44.09. So 1.5 divided by 3 and divided by 44.09. This one comes out to be 0.011340444, are all the digits I see on my screen. Now I'm going to do this one, 35, with an exponent of minus 3. Oh, minus 3. That's that number, times 6.26. And then I want to divide it by 20. And this one comes out to be 0.0100955. That's a 0. So 0.01, comparing these two, this now is my limiting reagent. So my answer is going to be this number times what's under my question mark is 10 times 152. Okay, now, so I've got that number on my screen. Now, if this one, the other one over here, had come out to be the limiting reagent, with me, I wouldn't now have had this copied down. I'm just doing this for you to see. And this would be off my screen. So what I would have done right here is just go right back there. 1.5 times divided by 3 and divided by 44. That would give me this number if it's the limiting reagent. Then I would take that times this times this. What I'm trying to tell you is do not round off your rebalancing factors. Keep all the digits. And if you have to, re-enter the calculation again. Most of you will have calculators where you won't have to do that. So I got this number on my screen. I just say times 10 and times 152. And I'm coming out with 16.6516, and it's going to be in units of grams of the chromium-3 oxide. And if I'm rounding off, that is 3 significant figures in my problems, and that ought to always. And the volume was 35 milliliters. That's 3 significant figures. The molarity is 3. So it looks like 3 significant figures. So I'd round off there. I would round off to 16.7 grams of Cr2O3. Okay. All right. Now, you see how to do the stoichiometry problems, if there's volume and molarity involved, the only thing we're going to do is volume times molarity equals moles. Okay, and I'm going to work the problem through in moles. If it had said something like, what volume of 6.26 molar chromic acid would you need to prepare 16.7 grams of this compound? Then I would put the 16.7 grams here, divide by this and this. That would be my rebalancing factor. And then I would take that and multiply it by 20. That's the number of moles. And then I would use this relationship. I'd know the number of moles. I would know the molarity given in the problem. I could solve for the volume that I would need to do that. So no matter how you're doing the problem, this is the relationship that you're going to use somewhere in the problem if it involves molarity and solutions. So that's the only difference we've done, is just added that relationship to there. Now we're going to do some other, let's see, I need to escape out of this, and I need to go back and share the screen with you. The next thing we're doing is we're going to do a process that's called titration. And titrations are a very good analytical procedure for doing these types of problems that we've talked about, you know, on the checkpoint that we just did. We might do them in a process called titration, and it uses a burette. Now, burettes are very good. They have 2 decimal places generally. So if your volume is up here somewhere, you're measuring, say, between 1 and 2 milliliters on the burette, you're going to have at least 3 significant figures in that answer. But you're doing it by difference. And the difference is always going to have 2 decimal places. You know, you've got 2 decimal places up here and 2 decimal places down here. You're always going to have 2 decimal places. So it's a very accurate way of making measurements. And typically, in a lab situation like this, using a 50 milliliter burette, it would always have at least 4 significant figures usually. So it's really a good technique for making fairly accurate measurements of calculation of volumes involved in solution reactions. Now, what you're going to do is you're going to have one of your reactants in the burette, and the other one is going to be down here in a little flask. We usually use an Erlenmeyer flask because the way it's shaped, you've got most of the solution down there near the bottom and a small opening at the top. That allows you to shake and really vigorously shake that solution as they mix to make sure that everything gets reacted thoroughly, that you put out of the burette into the flask and cause a reaction. So you want it to be, you want it to react completely and quickly. So all the time you're doing a titration with one hand, I'm right-handed, so I manipulate the, I put my hand, like if you're looking at the burette now, I would be using my left hand, and I would reach around it so that my thumb and my fingers are on this little stopcock here that can be turned. You can turn this, and if it's turned straight down like that, the solution runs through very rapidly. If you turn it 90 degrees to that, you close off and nothing flows. So you can regulate how fast liquid is coming out of this, say with your left hand. You can turn that stopcock to make it either fast or slow. And in the beginning, you would want it to be very fast. And near the end, when you're almost done using up all of your limiting reagent down here, you want it to be very slow, because you don't want to miss the point when you've added just enough of this to use up every bit of that. And so you can regulate that with your left hand. With my right hand, I've got the Erlenmeyer flask in my hand, and since I'm right-handed, I can swirl that and shake it really, really good, and I can have the slow, precise control with my left hand of how fast stuff is coming out. So what we're going to do is notice the way that the burette is labeled. 0 is at the top, and at the bottom there's a line that's 50. If you go from 0 to 50 with the meniscus, you have transferred exactly 50 milliliters, 50.00 into the flask. And if you know what the molarity is of the solution, you can then tell how many moles of reactant you put in and going from 0 to 50. Now, if you run that past the 50, guess what? You got to start all over. There's no calibration down here. There's no way to judge how much you went over. So you never want to go above 0 or below 50. You want to start out somewhere near the top. Now, let me give you some practical things that I would be teaching you in lab if we could do that. But I've seen students take, I don't know, minutes to get that meniscus exactly on 0 up there. You know, we're going to do by difference. We don't really care that that's exactly at 0. So what I'm going to do when I get ready to do the titration is I'm going to take the burette, I'm going to clean it real good, and then I'm going to rinse it with deionized water, and then I'm going to pour some of this solution in it, swirl it around real good, maybe lay it on its side and roll it so I've made sure I got all the water out and got that solution, and I'm going to then run it all the way out the tip and discard that. So with that away. But I want this to be rinsed with the solution I'm going to put in it. And then the next thing I'm going to do is I'm going to just get my source, my stock solution, and I'm going to pour it in till it's somewhere close to the top up here. It doesn't have to be right there. I can put it right there. And then I can read that initial volume here. And when I get done, it's down here. I can read the final volume, and I know how much has been delivered out the tip. And I don't waste the time going, trying to get that exactly at 0 up there. Anywhere up there within the top 3 or 4 milliliters, and usually you can just pour it in. You say pour it in until you see it up in here somewhere, you stop pouring, well, some may wash on down and wait a little while, and it'll settle out some reading up here, and then you take that reading. It doesn't have to be 0. Next hint. When I'm beginning this reaction, I want to flow this through as fast as I can. Now, how do you know when you added just enough of this reagent to use up all of this? Well, you have to have what's called an indicator. Something that is, say, one color, it's a dye, that's one color in this solution and a different color in this one. So that when you come down through here and this is all gone, let's say we're doing an acid-base titration and this acid is down here and the base is in the burette. Well, if I put an indicator called phenolphthalein in that flask, then it will be colorless in acid, but it's bright red, really pinkish red in base, and in the sodium hydroxide, maybe, or whatever base you got up here, it would be red. So this is going to stay colorless, but as I'm running this through, right there where that's hitting, it'll be pink, because the indicator that's the acid hasn't all been used up in the little stream that's coming down into here. So it'll be pink around that. Now that's the reason for me having my right hand down there shaking it. I'm going to shake that, and I'm going to run this through as fast as I can, wide open, until I can't shake the pink color out. Then when I see that happening, I'm going to close off the burette and keep on shaking and see if it does come back colorless. If it does, then I know I still have to add more base to it. Now, instead of it being wide open, I'm going to add it slower. And I'm going to just change that stopcock over here to get a really slow rate. And as long as I can shake it down, I will keep that slow rate going. But when I can't shake it down anymore, I'll shut it off, see if it stays colorless. If it does, I need more, and I will start flowing it a little slower. Now, truth of the matter, here's what I'm going to do. I'm going to read this reading. I'm going to open the stopcock wide open. I'm going to run it in there as fast as I can. When I can't shake it down, I'm going to stop. If I'd done, most of the time, I would have overshot the end point and it'd be pink. Well, I don't know how much I put in extra, but I can tell how much I put in. Suppose I put in 37 milliliters of the base. Well, I know that's too much. So what I'm going to do is throw that sample away, put in another sample in my flask down here. I'm the same amount that I put in the first one, by the way. And then I'm going to run down through here, and maybe at 30 milliliters, I'm going to stop and shake it down. Now, if I'm lucky, that one stays colorless. And I would open the stopcock very slowly, again, shaking as hard as I can shake. As long as it stays colorless when I'm doing that, I'm okay. I'm going to slow it down. I'll eventually get to a just drop falling in at a time. Drop and drop and drop and drop. Well, when that one looks like I can't shake it down, I'm going to stop. And if it's really light pink, I'm done. And if it's still not enough, then you can actually go and right down here, you can open that stopcock just a tiny little bit and have a little half drop hanging on the bottom of your burette. And you can just tip that over, tip the flask over, put that little drop on the side of the flask. Take your wash bottle of water, deionized water, wash it down in there, and maybe that'll just be tiny, very slightly pink. If that holds for 30 seconds, you're done, and you have gotten to an actual fraction of a drop of what the endpoint could be. Now, the endpoint is when your indicator changes color. That's not necessarily the equivalence point. For example, in phenolphthalein, the phenolphthalein changes color from colorless to pink about pH 10. If I'm titrating NaOH and sodium hydroxide, I'm going to get salt water at the end, so I expect the pH to be 7, neutral, like water. So actually, I would miss the equivalence point. I would go over it just a little bit because my indicator didn't change till pH 10, and it's at pH 7 that I wanted. So I would be off a little bit with that one, but actually the amount is probably less than a drop. At the equivalence point, the pH rapidly changes. A drop could make 2 or 3 pH units. So even though we might not hit exactly the equivalence point, the end point is close enough for us in Gen Chem 1. Now, when you get to quant, they'll probably have you use methyl orange is pretty good for these titrations, and it would get you a little closer to pH 7. But you need to pick the indicator pretty close to the color change, pretty close to the equivalence point. And it's a little bit of a judgment call. We use phenolphthalein because the color is really easy. I told you methyl orange. Well, it's orange at the equivalence point. It's red in acid, and I think it's green or blue in base. I think it's green. And there's a little flash of orange in between those when you're at the equivalence point. So it's a much better indicator, but the endpoint's harder to see. Pretty easy to miss it. So we use phenolphthalein here because it's much, much better. Okay. If you'll remind me, When we're not recording, I'll tell you a story. A story I'm going to tell you I can't record. Okay. All right. Now, suppose we had something that looks like this. My initial volume, I've read this, and remember the burette is reading downward. So if your meniscus is between 2 and 3, it's 2 point something. And you read from here down to there would be 2.5, and then 2.6, and it's almost at 2.7. And I estimate this last significant figure, 2.68. Now, here's a point. If I'm doing a lab, I would count off credit if you just wrote 2.7. That burette, if it's 2.7 exactly right, 2.70, I've had students go up here and the initial volume, they write down 0 milliliters. I mark significant figure error. It is. It's 0.00. Okay? So you do have to have 2 decimal places in every burette reading. And that was a question on one of our first labs, I think. And then somewhere down in here at the end, there's 46, there's 47. So it's somewhere that, and it looks like it's a little more than right at the 0.5. So I read it 46.48 as the reading here. The amount of stuff delivered is the difference between the initial and final reading. So the volume is 43.80 would be the actual volume. And I used this deliberately because if you subtract these two numbers out, your calculator will show you 43.8. But it's a burette reading. It has to have 2 decimal places. So you'd have to put that 0 in. Okay? So it's 4 significant figures here instead of 3. You want to make sure the decimal place is correct. So that's how you do titration. The equivalence point occurs when you've got the correct stoichiometric amounts of each one are brought together. Nothing's in excess. Everything's used up. The end point is when your indicator changes color. So we do distinguish between these two. If you're using an indicator, then the end point is when your indicator changes color. It's one color in one of the reactants where it's located, and then you're adding the other reagent, but when you put it in the other reagent, it's a different color, and you'll see that color change. You want the color change to occur close to the equivalence point. So you want these two to be as close together as possible. And for precise work, there's a whole host of indicators that you can use. You can look them up, and you can tell the pH at the end point for every one of those indicators. And then if you know the pH at your equivalence point, which we will be calculating next semester, you'll know what indicator would be the best to give you the most accurate reading. Okay. All right. I believe that's all for this lesson. Our quiz is Monday, and we've got today's Wednesday. We got tomorrow. I believe we're okay to stop right here, and oopsie, and I will stop the recording.